Let's begin with the fundamentals of MPPT first. After that, we just move to the fuzzy logic based MPPT technique. The maximum power point tracking is a technique used in solar PV systems to extract the maximum possible power under varying environmental conditions. Since PV panels have non-linear IV characteristics, their power output changes with radiations and the temperature. This means the power of maximum, or you can say the point of maximum power point, or you can say MPPT, shifts throughout the day. The MPPT algorithm dynamically changes or adjusts the system's operating point or track this MPPT. Without MPPT, energy harvest drops significantly. The fact is this implementing MPPT can increase energy output from 20% to 30%, making it crucial for cost effective and efficient solar system, especially under varying environmental conditions. Now we move to the next slide for today's topic, that is our fuzzy logic based MPPT. Now let's first understand fuzzy logic, the core of our MPPT method. Unlike traditional binary logic where variables are either true or false, fuzzy logic works either with degree of truth, values between 0 and 1. This allows system to handle imprecise or uncertain data, it mimicking how humans make decisions. As you see in the diagram also, we have some components like fuzzy interface engine are there, fuzzy rules are there, defuzzifier system are there, output membership function, input membership function are there. So we discuss these one by one in the future slides. This fuzzy logic is basically a expert system. It just based on the observation of a human, how it how he just write its membership function, how he just define the rules for this. So this fuzzy system is introduced by Lotfi Jade in 1965. Fuzzy logic is ideal for complex non-linear systems like PV array, where driving accurate mathematically models is often difficult. A fuzzy logic system typically includes fuzzification, membership function, rule base, interference engine, and defuzzification system, which convert fuzzy output back into precise value. Now, we just first discuss fuzzy logic MPPT working. So, as you see in the diagram also, we just introduced fuzzy logic MPPT. It just extract voltage and current from the solar PV and it just adjusts the duty cycle of the DC-DC converter. So now let's apply fuzzy logic to MPPT. In fuzzy logic MPPT, we track the MPPT using two input variables. First is error, that is equal to change in power divided by change in voltage, essentially the slope of PV curve. After that, we just go with change in error, that is known as delta E. It is equal to error at an instant, let's say k, minus error at the previous instant, let's say e k minus 1. Rate of change of slope. We just check out here. The output of fuzzy controller is known as change in duty cycle, that is known as delta D. The change in duty cycle of the DC-DC converter, it just fed to the converter First, in this process, first we measure voltage and current from the PV panel, calculate power, after that drive the error, or you just find out the error, then find out the change in error, use fuzzy membership function to fuzzify these values, apply the fuzzy rule base to drive fuzzy output based on the experience of the human. Defuzzify this output to get a precise duty cycle. Update the converter duty cycle accordingly. This loops runs continuously, adjusting the operating point to follow up the MPPT even as the environmental condition varying. Now we move to the implementation of the fuzzy logic, how to implement this. We actually implement fuzzy logic MPPT. In the first case, we define the inputs. Inputs are error and change in error, and the output is change in duty cycle. There are various representations like negative big, negative medium, negative small, zero, positive small, positive medium, positive big, as you see in the diagram. Here is my error, here is my changing error, and we just find out. It is up to you how many linguistic variables you just choose. You also choose very negative big, very negative big, is it is up to you. In the next, we design membership function for each input and output. Then we establish a rule base. Usually it takes 25 to 49 if else condition or if then rules based on the expert knowledge. And here the expert is human or we. We use Mamdani interface method for rule processing and the center of gravity method for defuzzification generally. It is up to you which type of rule you just use and which type of method, interface method, inference method you just go with. The accuracy of MPPT controller highly depends on the quality of these rules, how well the membership functions are defined in the fuzzy logic. Now we just move to how to implement the hardware section. To run this algorithm in real time, we need suitable hardware. A PV array as a simple input source in which there are series and parallel combination of different solar panels, a DC-DC converter to regulate the voltage, a microcontroller or DSP, digital signal processor, to compute the fuzzy logic steps where our algorithm just run. Voltage and current sensor for accurate feedback. Accuracy plays a main role over here. Your sensor should be accurate. A gate driver to control the switching of power electronics device. Some practical consideration include like fuzzy logic require more processing power than simple or traditional MPPT like PO and INC. We need high sampling frequency here. It varies from 1 to 10 kilohertz to ensure fast response. Sensors must be accurate, especially for computing error, change in power to the change in voltage. Memory is needed to store the rule base and membership function. And timing is also crucial. If we respond too slowly, we miss the MPPT. There are some advantage and disadvantage of our fuzzy MPPT also. Let's evaluate. Advantage is provides higher tracking efficiency than conventional methods like P&O, INC, fast response to change in radiation and temperature, minimal oscillations around MPPT, performs better under partial shading condition. It doesn't require an accurate mathematical model of the PV system. In the conventional systems or conventional MPPT methods, we require accurate mathematical model of the PV system. In the diagram, as you see, here is the tracking efficiency, response speed, stability, complexity, partial shading performance, implementation ease are just verified through the hexagonal graph. There are some disadvantages also, complex to implement due to fuzzy logic system design, need expert knowledge to define effective membership functions and rules, higher computational and memory requirements. Performance is highly sensitive to design of the rule base. How many rules are there and how you just create these rules. These are accurate or not. There are some practical applications. Fuzzy logic MPPT is used in applications where efficiency, adaptability, and reliability are essentials. Grid connected PV systems where tracking accuracy improves ROI, rate of interest, or you can say rate of improvement. Off grid systems in unstable environments, building integrated PV, that is known as BIPV, with complex shading profiles, electrical vehicles where real-time optimization is crucial, space applications where power system must be extremely efficient. It is ideal for large solar farms, portable solar farms, hybrid systems, solar plus wind, smart microgrid and IoT connected platforms, power platforms. There are comparison with other MPPT also, as you see in the graph. P&O is simple but suffers from oscillation and slow response. INC is more accurate but slower and still limited under partial shading conditions. Fuzzy Logic MPPT adapts better to fast changing environment and it is more suitable to partial shading condition. It is more complex but delivers better efficiency. It provide efficiency up to 97% compared to 93 to 95 in the case of conventional like P&O and INC. Smarter decisions thanks to its human liking reasoning. Reduce energy loss due to quicker settling around the MPPT. Now we move to the conclusion. Fuzzy Logic MPPT leverages AI inspired decision making to dynamically track the maximum power point. It handles non linearities, partial shading, and rapid environmental changes with better precision than traditional methods. The key to success lies in the decision of rule base and membership function that we define in the while designing the fuzzy logic system. Looking ahead, we are moving towards neuro fuzzy systems for adaptive learning, FPGA, ASIC based implementation for real time performance, IoT connectivity for cloud based optimization, multiple object or multi object fuzzy logic, which balances energy efficiency, reliability, and system lifespan also. This is all about today's lecture. Thank you.